we've seen how to construct an unlabeled and unscaled sine graph. So how do we scale it or label it? And I should say scaling or labeling, which really means the same thing. Unscaled sine graph. So here we have a sine graph. Now I've got some scales on it, but it was originally unscaled. And I want to put a scale on it. Well, we know that your basic y equals sine theta graph does have a scale where you have 2 pi here and -1 here and 1 here, as we saw before. And the 2 pi simply corresponds to the circumference, to the arc distance of a point on the unit circle, the arc distance of a point from the positive x-axis on our unit reference circle. Again, we saw that previously. And that is a measure of radians. Now, for any reference circle, larger or smaller, the measure in radians is the same for any angle with a positive x-axis whose arc is measured on the unit circle. I didn't quite say that right, but I hope you get the idea. Okay, so what we're going to say is that for an unscaled graph, the phase at this point is always 2 pi radians. And the phase, when we come around, all the way around the circle, is always 2 pi radians. Again, we've seen why we have to do that, and I've indicated much deeper reasons why that's necessary. Haven't gone into a lot of detail on those reasons, but again, this point always corresponds to 2 pi radians on your reference circle. Okay, so what if we want to label a graph that still has just the 2 pi radians around the reference circle, but has -4 here and 4 here, as I've indicated in the orange chalk? What would our function have to be? That would no longer be y equals sine of theta, because the sine of theta only goes from -1 to 1. This function is going from -4 to 4. Well, it makes a certain amount of sense that if we multiply sine of theta by 4, then this point and this point, the point where the sine is lowest and the point where the sine is highest, will be at -4 and 4. Now, if we do that, the graph of the original sine function, y equals sine of theta, according to the orange labeling, the graph no longer corresponds to y equals sine of theta. Y equals sine of theta would be, well, what we get when we divide all the y coordinates of this function, y equals 4 sine of theta, by 4. Well, we can actually construct that. If this is now the graph of y equals 4 sine theta, then the graph of sine theta, well, we cut this interval in half, cut this in half, and the sine function takes its value +1 here, and we're going to have same construction down here, and -1 here. And now, okay, let me actually do that. In the color that matches the labeling. So this graph corresponds to for the labeling where -4, where your y values range from -4 to 4. So for the white labeling, where I've got this labeled 2 pi and this -1 and 1, this still corresponds to sine theta. But for the orange labeling, this graph now corresponds to y equals 4 sine theta, and this graph would be the graph of sine theta, every point here being 1/4 as high as the point on this graph. Now, another labeling. Okay, and this one actually has an interpretation. In yellow, y goes from negative 30 centimeters to 30 centimeters. So the negative 1 and 1 points of the original y equals sine theta graph are negative 30 centimeters and 30 centimeters. And the time corresponding to this phase of 2 pi radians, in other words, this complete cycle, is 1.6 seconds. This corresponds to something that goes through a complete cycle in 1.6 seconds. We've seen things that go through cycles on times of that order. Pendulums. Okay, we've seen pendulums that have cycles around 1 second, around 2 seconds, and for times in between, and sometimes would be fairly close to 1.6 seconds. And if you measure the motion of a pendulum from some central point, the pendulum could go from negative 30 centimeters to positive 30 centimeters. So a pendulum could go from extreme points at negative 30 centimeters on one side of equilibrium to 30 centimeters on the other side, and have a period of 1.6 seconds. Now, what would our function be? Well, in terms of what we saw before, it should be fairly evident that we're going to need 30 centimeters multiplied by values of the sine function. Now, values of just plain old sine function go from negative 1 to 1. If you don't multiply it by something, the values go from negative 1 to 1, whatever's inside the parentheses here. The question now is, what goes inside of the parentheses on the sine function? It's no longer theta. In the first place, it's a time, and we're going to indicate time by t. Well, in this case, I'm going to say, okay, well, t equals 1.6 seconds when theta equals 2 pi. I could just write 2 pi, but I'm going to write out the radians. When theta equals 2 pi radians. So that, in a sense, we can say that 2 pi radians is equal to 1.6 seconds. Okay? So that 1 radian is 1.6 seconds over 2 pi. And 1 second equals 2 pi radians over 1.6. So that when the clock reads t, the phase angle theta reads 2 pi radians over 1.6 seconds times t. So that the sine of our phase angle is going to be the sine of two pi radians over 1.6 seconds times t. Now, I actually don't think that was the clearest possible explanation. So I'm going to stop here and continue in another video.